Hi everyone, how are you going? Look, my name's Adrian McCallum. I'm from University of the Sunshine Coast in Australia, and I very much appreciate the opportunity to speak with you all today about this work on estimating subsurface snow density using ground penetrating radar and the surface reflection method. So look, a bit of context initially. Um, I'm not necessarily a radar specialist. What I tend to specialise in is the assessment of snow mechanical properties using the cone penetration test. So in these images here, you see a picture of a CPT mounted to the rear of a tractor, where I typically force the cone down over 10 metres depth in the Fern, Antarctica. And the tip of the cone and the friction sleeve on the cone can help us assess snow physical properties. And on the graph on the right here, you get a measure of tip resistance down to here, 5 metres. And you can see some melt layers, you can see an increasing in the hardness of the snow as we go deeper, etc. So the CPT, of course, is a point measurement. It's relatively rapid and easy to do, but you only get data vertically beneath the point in which you insert the cone. So an obvious extension of that, of course, is, well, could we use something like radar to extrapolate or interpolate between point CPT data to depth? So whilst I was doing that work on the Brunt Ice Shelf in Antarctica, I dragged a 400 megahertz radar behind a skidoo to try and tie up or tie in the CPT data. So the image on the right just shows a couple of radar traces, or a radar trace. And what I was trying to do was, of course, align stratigraphy and hard layers that were identified by CPT data. You can see that in the light yellow and the blue. And I was trying to tie those together with ground penetrating radar. And that's to some extent a work in progress, but as you might expect, where there are changes in stratigraphy and hardness or density that are picked up by CPT, then generally, yes, you can expect to tie those together or extrapolate those data spatially using something like ground penetrating radar. After I finished that work, then I came back to the University of the Sunshine Coast here in Australia. And as you can see from that image, whilst there might be plenty of kangaroos around munching the grass, unfortunately, there's not much snow to conduct continuing snow research. So I started looking around and thinking more about what quantitative methods were out there to investigate the GPR data that I had, that I'd previously collected in Antarctica. And one method that I essentially stumbled across was a method called the surface reflection method, which was, as I understand it, originally devised in Scandinavia for road pavement assessment, and has also been used extensively in the United States to assess, again, road pavements. And the basic concept of the surface reflection method is that if you take a radar, but in this case, it's not a ground coupled radar, it's an air coupled radar. And if you essentially calibrate that radar by holding it over a metal plate in the first instance, then you can assume that you get an almost 100% reflection back to the radar. So you're assuming that your metal plate is a perfect reflector. Then via this equation on the right here, you can then compare the amplitude of when you drag that radar in an air-coupled form over any other surface, whether it's a road pavement surface, a concrete surface, or indeed, as I'm about to describe further, potentially a snow surface. And then by doing the basic maths to the right there, by comparing amplitudes, you can estimate the dielectric constant, and from that, the density of the snow. So I've written about that, assessing surface snow density using the surface reflection method. But this talk today, I'm taking that one step further to look at, well, yes, we can probably assess the density of surface snow using the surface reflection method. Can we also suggest the probable density of the snow beneath that surface layer? So that's what I'll speak on a bit more now. So looking at this diagram from Scullion in 2001, this explains the scenario a bit more. On the left, we have an air-coupled radar antenna, and we've got numerous reflections there, A0, A1, A2, A3. And those reflections are either internally from the radar, from the surface of the medium, whatever it might be, whether it's snow, asphalt, whatever, the return from the first interface, which is A2, and then the return from the second, or in my case, a base interface, which I'll explain shortly. So merely by comparing the amplitudes of those returns with the assumed perfect reflector, the amplitude from that perfect reflector, then we can get a feel for relative returns, and the time taken between those returns, of course, can give us an estimate of the depth of those layers. So that's the basic premise of the surface reflection method, comparison of amplitudes, assuming an initial perfect reflector. So if we put all of that together, we can determine surface layer thickness, H1, by using the simple equation in the top right of the screen there. Once we've got surface layer thickness, we can then also estimate base layer thickness using the simple equation in the bottom left of the screen. And in the bottom right of the screen is an equation for the base layer dielectric, which again can relatively easily be calculated using that equation, using data that we obtain from field measurements, as long as we have the dielectric of the surface layer. So again, in the bottom right, once we've got the surface layer dielectric through that equation, we can then estimate the dielectric of the base layer. So how did I test this? Well, as I said, there's not much snow out my window at any time of the year. So opportunistically, I was in the Australian Alps, which coincidentally has some of the greatest snow cover in the world. It's just not particularly thick. So this image on the left shows a Mahler 900 megahertz radar sitting on top of an upside down plastic container, essentially to hold it statically in an air-coupled manner, and that's held over about a 1 meter thick snowdrift, which is over an asphalt base. So it's a car park which has been covered by snow. I've cleaned off the end with a shovel to get a face there that is about 1 meter in thickness or in height, and there's only 2 layers there. So one homogeneous layer at the top, one relatively homogeneous layer at the bottom, and the division between those two is separated by the point that I've named there, A2. So on the right hand of this screen is the wiggle trace from the radar held statically in that point. And again, on the wiggle trace, I've marked A0, A2, and A3, and they respectively are the end reflection from the radar. A1 is obscured. A2 is the return from the first interface, which you can also see on the image to the left. And then A3 is the second or base interface return. So again, all we're aiming to do from that radargram is look at the relative amplitudes that you can see there and also compare the time between those amplitudes. And if we do that in accordance with those equations that I showed a couple of slides earlier, then this is what we get. So on the left, we've got 3 layers there, 1, 2, and 3. They're measured thickness, merely using a ruler, a tape of 0.63 meters, then 0.17 meters, and the final layer of 0.1 meters. Then there's their estimated thickness using the surface reflection method, and to the right-hand side of that table is their measured density using gravimetric density measurement, taking out sample and weighing it. And on the right-hand side is the estimated density using the surface reflection method. So what I've done there is circle in green those results which are favourable. So the thickness of the first layer, it was measured as a thickness of 0.63 of a metre, and by the surface reflection method, we come up with a thickness of 0.62 metres. So that aligns nicely, of course. The measured density gravimetrically was 587 kilograms per metres cubed for the top layer, and estimated using the surface reflection method was 578. So again, nice and close there. For the second layer, measured thickness was 0.17 of a metre. Estimated thickness 0.63 of a metre, so something's gone awry there. That's certainly not as close as we might like. But when it comes to density, the measured density of the second layer was 555 kilograms per metre cubed, versus the estimated density of either 515 kilograms per metre cubed or 558 kilograms per metre cubed. So both of those are fairly close, and the superscripts there just indicate that I've used 2 different equations there to estimate snow density from dielectric constant, which we get from the surface reflection method. So we've ticked 3 boxes there. We're missing the 4th box, so further work is necessary to refine that. It's not work that I can easily do. It's still on my to-do list, but hopefully some of you out there who might have a radar sitting in the corner of your room and some snow outside the window, if you get an hour even, you might have the time to validate whether the surface reflection method might work for you. It's relatively easy to apply, and I think it has great promise for determining snow thickness either spatially or temporally, and I'll speak about that briefly now. So of course, with the ubiquitous use almost of UAVs and UAV mounted GPRs, especially potentially SDR or software defined radio form where they're light and easier to transport, then there might be the opportunity to put an SDR GPR beneath the UAV, set it off on its own path to track snow over a large spatial area, and certainly probably pick up surface density variability across that area, but also via this method perhaps pick up subsurface density and also layer thickness with regards to that area. Or if you didn't have a UAV handy, you didn't want to examine density variability spatially, you may be aware of a new paper that came out earlier this year by Peters et al. In the group from Stanford University, where essentially they were using an SDR GPR that was operating passively and using the sun as the transmitter. So their research essentially suggests that you can put this very small, lightweight, battery-powered SDR GPR on a snow or ice surface. It can sit there for a period of time, and by discriminating between the direct returns, the returns directly from the sun and those returns from the base interface, then you can measure the thickness of the ice or the snow depending on the material that you're sitting on. So this might be one way in which you could potentially use the surface reflection method to put a passive radar on a snow surface, let it sit there potentially for 6 months or as long as your battery lasts, and you could in real time perhaps measure both the thickness and the changing density of that snow surface and potentially of base layers of surfaces beneath that initial snow surface over time. So that's something that I think might be one way to tie in this brand new work from Peters et al. With the work that I'm briefly speaking with you about today. So takeaway messages, does it work? Well, yes, for the surface layer, as per the table that I showed you earlier, it appears that both density and thickness could accurately be resolved. For the subsurface layer, density was resolved, which was great, thickness less so. So as I said, I, or perhaps you, we, perhaps could do some more work to verify that this technique is useful. If it's useful statically, then also hopefully it could be extrapolated spatially using things like UAVs. And as I just discussed, with the innovation of passive radar, particularly SDR passive radar, could we potentially put a very lightweight, cheap radar semi-permanently on a ice or snow mass and then let it return to us real-time changes in density and thickness in surface and subsurface layers. So that's it, ladies and gentlemen. Look, I very much appreciate your time. Thanks for the opportunity to share with you a little bit about my work at this online joint conference. It's a great pleasure to have the opportunity. My contact details are available on the web or probably via the conference proceedings here somewhere. If you do have any questions, I'd love to speak with you further, and I hope we get the opportunity to meet face-to-face at a similar future conference down the track. Thanks very much for your time.